So first, a little bit about us, just enough math. So my name is Ahmed. I'm a software developer here at Improving, and this is
Justin, math teacher, Lone Star College, data science enthusiast.
I waited until 2 to 5 pizza before making a talk, so you kind of jump right back.
What's wrong with being late?
He's a great guy.
That'd be good. So yeah, and so yeah, we pretty much this whole group is about just like math tools that'll aid in software development, right? Whether it's areas in just testing, algorithms, data analysis, that sort of thing. Pretty much the whole gamut, anything where there's some useful math tools that can make your life easier. We want to present them. And the goal here is really, just like the group is called, the goal here is to present just enough math to identify problems, get an idea of what the solution can be and where to look next, right? So we don't necessarily, even though Justin does do a deeper dive in some areas to give you a little more insight, the whole idea is if we'd be able to walk away with like a high-level conceptual understanding and actually packages that do things for you, right? So just understand like, hey, I know what this is, I know what it can do, I know where to look next, I know the thing.
Yeah, the truth of the matter is you don't need like a deep understanding of a lot of these concepts that are applied. You just do need the high-level understanding in order to properly, implement a package, some software is a package. So. But there are pitfalls, right? Like you can, without some understanding, you can sort of run off the rails and end up with results that are not valid or not useful. So we're just trying to address that.
Cool thing. And so we're not necessarily experts in the topics, question. I've been programming forever. Man's been doing math forever. But like the specific areas we kind of get into, a lot of times it may be a little newish to us. Like, oh, hey, we haven't explored this little nook or cranny, right? So a lot of times we're learning with you, presenting ideas that we find, hey, this looks like it has some relevance. But it also means that if you have some ideas or you want to talk about it, feel free to definitely chime up. Let us know if maybe, you have like different opinion or be kind of just in the field. And yeah, let's have a discussion. Definitely want to think of this as more of a collaborative group. And again, all the code here is pretty much written just to be as clear and notebook friendly as possible, just so you kind of read it and just know exactly what's going on. So I'm not worried about efficiency, robustness, or good coding style. Just mainly, hey, is it readable? Is it obvious? Because I don't want to like lose readability, try to optimize, or have a whole bunch of error checking conditions that hide really the core of what we're talking about. Right? Not production codes. If you try to use this production code, well, use it at your own risk.
It's Python, right?
I mean, it is Python too. Like, there's a whole other.
I say that, but it's like the only language I know.
You do use some more.
Popular language right now. So
Yeah, it's Python.
Yeah.
Yeah. So for data science, it's perfectly adequate and common, widespread. And I do know how to use R.
I wouldn't say that too loud. Not too loud. I hate R. I've used it in that slides.
I don't know anything about that, but I know that the packages. I know that depends on the package that you're using.
You hate it, but
Huh?
you hate it,
It's just such a janky, messed up language. It's just, don't get me wrong, Python ain't exactly an example of like elegance and good design, but I think it's better engineered than R. R's got like a lot of just really just badly designed areas. I know there's like no real facilities even for things like unit testing. It has a lot of inconsistencies with how it handles functions. There's just a lot of stuff. It's got a nice ecosystem, right? That's kind of like the same thing with Python, right? Python's got a nice ecosystem. And that's really what kind of, helps it. But in terms of language itself, yeah. And then, yeah.
I wouldn't know.
everything I want to do, I find I can do it easier in Python. Like almost everything. It's really. It's not perfect, just like you said, but it's just it makes things so.
Yeah. It's more consistent.
I find manipulating data frames easier in R.
Our data frames aren't bad, but you have things like even trying to reuse functions as lambdas, even data structures in R. It's really kind of ad hoc, and not that Python's great, and you have to use dictionaries for everything, or classes, which is like structures. Yeah. That's kind of been my experience too. It's just that I find that Python, And here we use Python though mainly because, one, tons of libraries, right? Everything we talk about, there's a library for it. Two, it's easy to put in notebooks so we can share information with you and put presentations. But really it's the ecosystem, so I don't necessarily endorse Python, but it's got a very nice ecosystem.
And it's especially good when you're a topic like this, it's data science adjacent.
Yeah, exactly.
Because there's a lot of packages. Like sklearn is the package that we use today.
Yeah. We use sklearn, and we use a few other ones like NumPy and so on. We'll kind of talk about it. But yeah, and anything we present, it's not business advice. We try to present you with the pros and cons of everything, just so you have a better understanding. But of course, analyze your own case. And of course, for the beginning, any opinions are ours and not the opinion of our employers. And yeah, and we do use a few packages here. Don't let this import list scare you. So NumPy, if you're not familiar with NumPy is a very important one to know. We use NumPy, we use matplotlib to plot things, and then sklearn is where we're pulling in a lot of our PCA and a lot of our machine learning neural network code. So, okay, and so let us. I guess you wanna go ahead and take us into the maps of the casino data. Do you want me to steer, or do you want to steer?
No,
yeah. Okay.
So this is just a little bit of data that I'll just use in some examples down below. I'm going to make use of the casino data, the 2D casino data, and the 3D casino data. I think we're not going to use the correlated.
Yeah, we're not going to worry about that.
But I will talk about those data sets, and maybe I think I may update this sheet later to include those examples.
And I've shared links. Folks have links, so they should be able to access everything.
Right. So if I make an update, then you can see that. It's just gonna, right? That's how.
I'm gonna check see what's out there around the facilities. Why you can
Yeah, keep me one of those sparkling waters, raspberry, black cherry. All right. So what is PCA? So principal component analysis. We'll just take it calling it PCA from now on. Fundamentally, what it is, it's a method of taking data that has a lot of attributes, right? Say you've got like 1,000 attributes or something, and then reducing it to a short list of quote unquote attributes, which we'll get into why the quotes are there, but it's part of a class of methods called dimensionality reduction methods. Okay, so when we think about the dimension of the data, what we're talking about is really the number of attributes. And so we'll kind of get into the details of that here. So in this section called tidy data, data points, and feature space. So if you're not familiar with these concepts, these are pretty useful background concepts for understanding just the framework of what this method is all about. All right, so a little bit of like bookkeeping to get out of the way, or just sort of setting up terminology and how we talk about things, right? So you've got a data frame. So we're in this regime where we have we think of our data as being in a data frame. So it has rows and columns, right? So typically, you don't have to, but typically I find that people talk about the columns being your attribute data, and your rows just are being called what we call observations. So, so just to make it totally concrete, you can look at the 2D casino data, right? So this is a data frame where the attributes are listed up here. So we're talking about attributes of a casino in Las Vegas. And then floors is the number of floors that the casino has, and the number of bedrooms is the number of rooms that it has. So these are two attributes of a casino, right? And the rows are just sort of named with the casino names. That's not always included, but it was convenient in this case. So anyway, so that's the idea of a data frame, where the rows represent attributes of the thing that you're studying, and the columns are individual observations of specific items, in this case, specific casinos. So the Mandalay Bay has 43 floors and 3,209 rooms. Thank you very much. Oh, yeah, it's not. Thank you very much.
That's what was really
nice. So that's the way we're thinking of our data as being formatted. All right. So up here, there's sort of a table. I just kind of compiled a table of just things that are words that are thrown around basically as synonyms for row and column. So a row, yeah.
Also, every column is also a dimension, right? We also treat it as a dimension. Did you mention it also? Because we talk about dimensional reduction. Just another synonym if we don't.
A column is referred to as a dimension?
Well, if like remember we have 50 column data, we kind of refer to it as 30-dimensional data because then we reduce it to PCA, right?
Yeah.
So you think of a column as a dimension also.
We never really heard that, but okay, yeah.
Yeah.
So I did make a note that the dimension here is equal to the number of attributes in the data set.
Yeah.
So, and here when we say dimension, we're referring to like the number of dimensions in the space that we're thinking about. So like we're in 3-dimensional space right now. So if you have many, many attributes, say you've got 1,000 attributes, you're sort of thinking of each row as a point in a 1,000-dimensional space. Right? So, which is weird, and we don't like that. In math, we deal with that sort of abstraction as just as a matter of course, and we just learn to deal with it. And even though we can't visualize anything, we just learn to reason about it. But on the other hand, it's nice to look at things in terms of 2 or 3 dimensions because that's the way that our brains are sort of set up to handle information visually. And so we're going to see some examples of high-ish dimensional data represented in low dimension, 2 or 3 dimensions. By the way. So yeah, columns. Sometimes we call, we say they represent variables or attributes or features. Rows are observations or data points. Right? Data point is sort of but the idea of a data point sort of plays a special role here because we're literally thinking of the data as points in space, right? So PCA is a highly sort of geometric. It takes a highly geometric view of data, right? And feature space is the dimensional the space that we're currently imagining our data in. So in the case of 1,000 attributes, again, we say that feature space is 1,000 dimensions. If we reduce that down to 2 or 3, we can say that our feature space has been reduced to 2 or 3 dimensions.
And real quick, any questions? All that makes sense? Yeah, feel free to just jump in with any questions. Definitely, please don't be shy.
And I didn't explicitly mention what tidy data is, but it's really just data that's been formatted in this data frame format in terms of rows and columns. Might be a little bit more to that, I'm not sure. All right, so yeah, there's just an example data frame. So some examples of using this terminology. So in our example data frame, the first column provides only the names, so this was not counted as attribute. Actually, I mentioned this. The variables / attributes features are words in the rooms. We did obviously. Yeah, the feature space, we think of feature space here as being 2D space. That's a mathy symbol for some places it's like to use that.
Yeah, I don't like that.
Yeah, I find out. Depends on where you're from. So anyway, let's plot these points in feature space. Right? So that's 2D data. Right, so if we plot these, we see that we can have a nice visual representation of this casino data in an XY plane, right? Really nice and straightforward. We get the idea. We can even see sort of a little bit of clumping here. The MGM Grand clearly looks like some sort of outlier, right? So it's nice to visualize things in 2 dimensions. It's nice.
Of course, we can try to visualize things in 3 dimensions as well. It's not as easy, but so I can figure out how to do the hotel thing. But so here's data on casinos in 3 dimensions. But where did the 3rd dimension come from? Well, I added an additional attribute called gaming space. That's the space of the actual casino area. Right, so that's another attribute of a casino. Right? It's the amount of space they have for the actual gaming as opposed to other hotel amenities and rooms and whatnot. So I added where is that data frame? Did I not put it in? Well, anyway, it's there. So this is what adding another attribute looks like. We still have the floors and the rooms, but with this additional attribute, of course, it becomes a 3D space. And so that's that. But that's the limit of what we can visualize, right? So the way the dimensionality reduction proceeds is by something we call an orthogonal projection, which is basically if so it's nice. So orthogonal is sort of a fancy word that means perpendicular or at right angles, right? So it's from Greek. So just to get that out there, So I've got what I concocted here is just an example of an orthogonal projection of a data point onto that. This data point is sort of living in 2-dimensional feature space, but we may want to project it down onto this line, which can be represented as a 1-dimensional feature space, right? So that's what it looks like. I made a little movie for you. It's projected. It's not Python, it's decimals.
Yeah, it's linked, yeah. So you guys are pretty much linking to like an iframe that points to decimals. If you never use decimals, it's awesome. Please use it, it rocks. And with decimals, you can pretty much set variables, ranges to go over. As long as all created in decimals, you can access them separately. Then we just include it like in Python. Yeah, decimals is sweet.
Very nice.
Yeah, I only like decimals.
So yeah, that's the idea. So you can imagine any data point, right? I guess I sort of configured this thing so that I can toggle this data point around. So I can put the data point anywhere, right? And I have its projection here on it. It's kind of like a shadow, right? Sort of like this shadow. So any data point that I can imagine out here in 2D space can be sort of projected onto this line. And now I have sort of a 1-dimensional representation of my 2-dimensional data. Now, of course, inherent in that process is some loss of information, right? You can't just squish all your points down into a lower dimension and not expect to lose anything. Luckily, PCA has built into the process ways to quantify that loss. Okay, so that you can choose your standard. You can say, I want to maintain 90% of my original. It's often referred to as the original variation in the data. Sort of this explanatory variation that exists in the data. So you can tell the algorithm, I want to maintain this much explanatory power, essentially, and it will produce a result accordingly.
And you'll see how to do that in the packages, because there's built-in packages in Python. You can specify the amount to retain in your columns.
So just for the record, this projection process can be applied to arbitrary dimensions, right? So if I have 1,000-dimensional space, I can project that as 50 dimensions. I can project it as 2 or 1 dimensions. So we want to find the best thing, the most useful thing to do, but it's possible no matter what. Whatever you want to do is possible. So the choice is up to you. All right. So how do we choose our projection, more or less, is kind of the next question. And what we do, or one way at least of looking at this, is looking at the correlation matrix of your data. So a correlation matrix, or first I guess we should talk about a correlation. Right, so a correlation or more properly, a correlation coefficient is a number that is calculated from a specific formula, and it lands always between -1 and 1, right? And it measures how strongly related two variables are. Okay, so two quantities. Now, in the context of data, what that means is we're talking about two specific columns, right, or two specific attributes in the data, right? We can use this formula to calculate a correlation coefficient between them. Basically, it's an estimate of the correlation. Right? So,
Question?
yeah.
So just specifying, so we're talking about like the related, you're talking about their tendency to change together or change apart.
Yes. So relatedness it's even more specific than that, but so yes. So broadly, so big picture. A rough outline is that a correlation coefficient that is in the vicinity of 1 is considered a high correlation. That means that if one variable goes up, the other one will also tend to go up, and if one variable goes down, the other one will tend to go down. Tend to being the important statistical statement, right? So and on the other hand, if you have a correlation coefficient that's closer to -1, then they will tend to move in opposite directions. So think of like the classic examples, like temperature outside and lemonade sales. For your lemonade stand. The higher the temperature goes, the more lemonade you sell. That's a correlation. That's actually, I guess that's a. Yeah. So sorry, I was thinking of something. But yeah, so that's one example. Example of a negative correlation is what if something goes up and then something else as a result sort of goes down.
Like the more you have of something, the least valuable it is.
Mm-hmm. Yeah. So the more readily available something is, the less its value becomes. Yeah. So there's an inverse correlation. So that would be negative. We would call that negatively correlated. So, and then if you're in the vicinity of 0, then there's effectively no relationship to be seen. Now I have to give the obligatory. Well, technically, actually, what's being measured there is the linear relationship, which is the limit of the measure. Because you can have a curvy relationship, or a quadratic relationship, and a correlation coefficient may not pick up on that very well. So there are limits to correlations. All right, so what you can do for any two columns, you can calculate this correlation coefficient. So then you can construct this matrix of correlation coefficients where it's better just to show an example.
Yeah, let's see. What about let's just show codes. Did we have where it was scroll down here? Yeah, show codes. There you go.
Yeah, so here's a correlation matrix for the casinos. Okay, so I'm using the 3D casino data, where we have the three attributes: number of floors, number of rooms, and gaming space in square meters. So, basically, to read this, to know the meaning of a number, you just say, okay, take this number. It's 0.69. Kind of closer to 1, right? So that's a reasonably high correlation. So and that correlation exists between gaming space and rooms. So according to this, the data is very limited, but this is probably not a meaningful correlation just because the data set is so small. But this is indicating a reasonably high correlation between gaming space and number of rooms in a hotel.
Why do diagonals work? Can anyone guess? Why do we have one non-diagonals? Yeah, it correlates with itself.
Yeah, any variable, any quantity, of course, if it goes up, then it goes up. If it goes down, then it goes down. So they're in perfect correlation. Right? Any variable is in perfect correlation with itself. Right? So that's why you have ones across the line.
Yeah, the order doesn't matter, so it's symmetric.
Yeah, that's true. This is the calculation of correlation coefficient is a symmetric calculation. So, for example, the correlation between rooms and floors is the same as floors and rooms, right? It's the same. So it's always correlation coefficient is always a symmetric. Another thing that is a little bit inadequate about these notes is that we could also be talking about the covariance matrix. And that actually has implications for how PCA is carried out. So there is a version of this matrix called the covariance matrix, which is not scaled in such a way to have ones across the diagonal. It's left. So basically, the scaling is if you're curious, the scaling is dividing by the standard deviations. But if you don't do that, it's called the covariance matrix. All right. So I'll try to touch on that. So there's another version of this that would occur with the covariance matrix instead of correlation matrix. And I did link, if you're curious, I did link the covariance of the Wikipedia on covariance matrix here. So now that we know what a correlation is and what a correlation matrix is, let's just kind of talk about the role that they're playing here. So correlations between columns quantify redundancy of information, in a sense. All right, I know I take this with a grain of salt. That's sort of how I understand it, right? But you understand what I'm saying, I think. If two quantities, they tend to move together, right? They tend to be, if one goes up, the other one goes up, and vice versa. Then, in some sense, I could throw out one of them and still retain a lot of information, right? Does this make sense? So, because they're behaving similarly, even though they're different attributes, right? So they're related in such a way that they behave similarly. So if I throw one out, maybe I'm not missing too much.
Because we're concerned about the patterns in the data, not necessarily the quote-unquote data itself. That's essentially what PCA is doing for us.
All right, so that's pretty much a summary of what all is here. So we talked about all of this business, about the properties of correlation matrix, what correlations mean, and so on. So let's see, there's a pretty sweet video. So here's an exercise to illustrate the Desmos, use the Desmos visualization below to see what two columns of data look like if they are uncorrelated, positively correlated, or negatively correlated. So what I rigged this up so that I can kind of toggle this slider here and manipulate the correlation. Now that the value on that slider is not the actual correlation, so it's not like this precise relationship, but I can toggle it, and you can see down here how the actual correlation between the two columns of data changes. So again, we have two columns of data, so we can visualize, right? So two columns of data can be represented in 2D feature space. So here's a scatter plot of the data. This data, we see the correlation that exists between these two columns of data right now is essentially zero. Okay. Right, so this is at least an example of uncorrelated data. Okay. Uncorrelated attributes, maybe I should say more precise. So let's see what happens as I move correlation towards 1.
So increase their correlation.
So I'm making these two columns, these two attributes more highly correlated. So what's the correlation that's showing right now? It's about 0.79, right? So once again, this is not the correlation. This is just the thing that I toggle to have an impact on this. This is the true correlation here. All right. So what do we see here? We see that sort of a linear relationship between the two are being established, right? And in the extreme case, right? See that they just line up like that, right? So and of course, here the correlation is actually showing us precisely 1. So as I toggle the other direction, what do you think is going to happen? So again, this is where you see the geometry of what's going on here, right? This is why I say this is a very geometric look at data. So that's what that's a perfect negative correlation looks like this. What is this? I don't know what that is. Oh, I know what that is. Okay. I know what that is. Let me get my data. Oops. It was a set one. I think it was set one. Okay, just refresh. Yeah, it was set one. Okay, so now now correlation is back at 0, right? Keep your eye on the correlation down here, right? So here's what I'm going to toggle. I'm going to toggle for this value. What's going on is I'm stretching it out, right? So what's happening to the correlation? Nothing, right? Nothing's happening to the correlation. I can squish it down. Nothing's happening to the correlation. It's maintaining 0 correlation, right? We do this business too. I go this way and that way. Correlation remains 0. So to my view, it's just really down to the geometry in the sense that if you expand it out horizontally, or expand it out vertically, or squish it down vertically, or squish it down horizontally, that's not what correlation is all about. It's this being it's this sort of diagonal configuration, right? If you've ever done a linear regression, by the way, you can see like, so, like if your linear regression returns a 0 slope, right? That coefficient is connected directly to correlation. I believe correlation coefficient is used in that calculation. So, so even though you say there's like you might say, okay, well, but there's a horizontal line or something like that. There's a horizontal trend line. Still, that's considered 0 correlation. Right? Because what is a horizontal line? It just means it's a constant, right? It's an unchanging thing. So if one thing is varying on the x-axis, but it's not varying on the y-axis, there's no relationship. Right? So, all right. Was this my last project here?
Yeah, probably jump straight to that bridges.
Yeah, it's going to cover all these points. Yeah. So, okay. So this is a visualization of what PCA does. Some things have been added for dramatic effect. So here's a data set that you start up. Again, 2 columns of data. So we have a 2D scatter plot with a 2D feature space. Okay. So part of PCA often is to, well, actually I believe always, although I could be wrong about that, is to first center your data so that the data is sort of centered around the origin. Another way to say that is that it has all the columns are scaled to have or shifted to have a mean of 0. So you average them up, you get 0. So the visualization of that process, dramatic effect, is this. So I take my data and I put it down there. All right, so get rid of that. And actually, let me unlock. You can unlock the viewport by unchecking that. So center here. Okay. Then another part of the process, which is definitely considered optional, at least in my reading anyway, is to standardize the data. And this is what that looks like. And what you're doing is you're scaling the data down to have standard deviation of 1. So it just kind of deforms the data, kind of squishes it a little bit. Right? So far we haven't really done any PCA. This is like pre-processing for PCA. Then what PCA does is it finds the direction in the data that has sort of the largest variance. So the largest, people describe it in various ways, but sometimes people say the largest spread, and that is clearly sort of like this direction, right? The data is spread out in this direction. And from our experience with the previous widget, by the way, we can see that this data here is, it's fairly highly correlated. Okay. So what PCA is going to do is find this direction for us, right? And say, okay, this is the direction that where I can see the most spread. So if I think of it the data along this direction, that's where I see most of the variation. Okay. So, but here's another, the direction that's perpendicular to that may also be useful, right? And there it is. And so one way to look at PCA is to say, okay, now I'm looking at this data through a different set of axes, right? So I'm no longer using this x-axis and this y-axis to understand the data. I'm now considering this maybe as a primary, as an axis, and this as an axis. All right. So when I look at the data that way, you see how I'm kind of I notice the orientation that produces the maximal spread, right? My words are failing. But once you have that, maybe you don't feel like tilting your head anymore, right? So we just do this. And we say, okay. Now I've got, and this PCA does not actually do any rotation of your data or anything like that. This is for dramatic effect. But the point is that now the coordinates are do actually, the coordinates of this data do actually represent what the output of PCA would be. Okay, so these coordinates actually are what PCA. Okay. So in a sense, I guess PCA does rotate the data, although there's no rotation matrix or anything like that involved. But so it basically represents your data this way. And now I can just get rid of these axes, these contrived axes altogether. And so, well, let me clarify one point. I said that this is the output. The coordinates here are the output of the PCA, but that's if you tell your package or tell the algorithm that you want two components, right? If you say instead that I'm going for a dimensionality reduction, I'm saying I want only one component, right? So that's naturally going to be which component? Is it this one or is it that one? And it's going to be this, because that's where we want to capture the most spread that we possibly can if we're going to choose a dimension, right? And so that's where my next movie comes in. And so that's what's going to happen. If you tell PCA that you want one dimension instead of two, then this is what it's going to give you. And you can just throw out the y-axis. It's my dramatic effect. Just throw out the y-axis. Don't need it anymore. That's my data now. Right? Of course, there was some information loss, but the fact that I chose the direction of that gave the most spread ensures that I kept as much information as I possibly could, given that I'm going to reduce to one dimension. Cool? Make sense? And with that, we'll talk about this data that came from the internet about heart disease. And Ahmed implemented some PCA on this data and did some analysis of it for your edification.
By implemented PCA, I just called the package I was built into Python because I'm going to calculate stuff myself. I'm a programmer. So let's okay. So this kind of gets us a little bit more into like the practical applications, right? It's like what would you like? What could you do this? What could you do with this? So I decided to do a machine learning task, okay? And we're going to build a neural network. And again, my build, we're going to use a package that's already built for us to predict heart diseases or heart conditions, okay? And so we've got some data, which I believe we pulled from cattle, and essentially this was data that actually was pulled from different hospitals, and it had a whole bunch of different measurements, like various like wavelengths on various monitors and all this other like medical stuff. And essentially it had a category of the condition of the heart. Okay? So you had and you have four possible categories in the data. You have normal sinus rhythm, which essentially is a healthy heart. And then you've got arrhythmia, congestive heart failure, atrial fibrillation, all of which are pretty much bad news, right? So the data is going to come with a whole bunch of columns, 54 columns of data, just various measurements. followed by a classification of what kind of heart condition people are looking at. One of 4 classifications as the code. So far, so good. So ultimately what we want to do is we want to be able to use this data to build a machine learning model so that if we get new heart data we've never seen before, we can go ahead and predict what kind of condition the heart is in, right? Which one of these 4 categories it's in, okay? So right now, I just pretty much just read the data, okay? And again, so this data consists of 1,200 rows and 54 columns, okay? And again, we kind of talked about columns and features, but you can also think of it as 54 dimensions, okay? And again, you can see a whole bunch of numbers, and then the 55th column, which we actually kind of sliced out, is the actual heart condition. So far, so good. Okay. So, yeah, so we have this ultimate goal of being able to build a machine learning model to predict, given these 54 data points, or rather 54 columns, we can figure out what kind of heart condition it is even for utterly novel data. Now, so the first thing we really want to do, a lot of times before building a machine learning model, it helps to kind of play around the data, take a look at it, get some insight into the structure. I mean, you can dive in and build a model, but it also helps to just, kind of visualize it a little bit. And normally the way we like to visualize things is by graphics. But this data consists of 54 columns, which means 54 dimensions. Which, I can't visualize 54 dimensions, I can barely visualize 3. So I want to try to see, hey, what can we do? So as it turns out, we could look at using PCA to actually condense our data down to 2 or 3 columns, 2 or 3 dimensions, and then actually plot that data, right? So we can actually take this data and visualize it. And as Justin did point out, we lose a little bit of information, but not as much as we think, right? So to give you an idea of what PCA can do for us. So first off, this little bit of code is pretty much how you can do PCA in Python. You instantiate the PCA object, that's pulled out of sklearn, and then n components here. It can either be the percent of the variance you want to retain, or it could be the number of columns. Okay, it'll see if it's an integer, it's going to be like, okay, number of columns. If it's like a float like this, it'll say, oh, that's the percentage, right? Yeah. Exactly, this guy right here.
This argument, what do you computer folks call it?
Yeah, argument, keyword, parameter, pick one. Yeah. And then we just tell them what solver we want to use, and we just use full solver. And then basically once we create the object here, then we can say fit transform, which will then transform our data into this lower dimensional space using PCA. So when we run this, right, so we're telling it right now, hey, 54 dimensional data, yo, PCA, go ahead and condense it, maintain 99.9% of our variance. And it says, sure, I can get rid of 40 columns of data and still retain 99% of it.
So this is the dimension of the new feature space.
Yeah.
If we maintain, so we've gone from 54 down to 14.
Yeah.
Right?
Yeah.
And maintaining 99.9% of the power.
Yeah.
It's there.
Exactly. So far, so good. Okay. And we can actually drop more and not lose that much. And the reason is because of diminishing returns. And I think this is something Justin put together. I can steer you can talk if you want on this bit,
sure.
But so right over here. So Justin produced this nice little graph giving you an idea of just what little you lose out of your data.
Yeah. So I forgot to rescale the axis. So this one should be over here. So all these numbers should be shifted over by 1. So here,
I think you're okay because you retain about 95% at 3. I think you're okay.
oh no, maybe.
That's about 60%, right? Yeah, 60% at 1, right?
It's like 60%. That's what it says.
Yeah, 60% at 1, and then you get to 2, you get up to 90%. That seems about right.
What I should have done is include 0.
Okay.
I should have included the word.
Well, the main
So,
thing is
okay.
diminishing returns.
Yeah, that's the main thing is the shape of the graph. So if you use the first principal component or the component and a synonym for component might be direction, right? Or if you look at the data along one direction in the first principal component, you get 60% of your explained variance. Now, if you up that to 2 components, you get whatever the difference is here. You get an additional, like, 30, but for a cumulative explained variance of more than 90%. Right. So if you're just looking at 2 dimensions at this point, your explained variance is above 90%.
So from 54 to 2 dimensions.
And then so on and so forth. But then you see is the more the more dimensions that you use, the less you're able to squeeze out. Yeah.
It matters, does it matter which dimension you pick, or is it
Yeah.
any arbitrary dimension? First one you pick, you get 60%, the next one, so on.
Yeah. So yeah, they're ordered in terms of explained variance. So what we call the first principal component, which is a particular direction, you can get the algorithm to tell it. Well, you can find out what it is if you're curious. But the point is that there is one direction called the first principal, the direction that the first principal component is pointing in, and that contains the most explained variance, and then after that is decreasing. So,
Brian had a question first.
But my understanding is like, let's say you go down to 3, that's not just choosing 3 random, like that's not choosing actual columns, that's just, those 3 columns are not existing in the original data, right?
Yes, absolutely.
Because those are basically 3 columns that are computed out of the other ones.
Yes.
right, yeah. So I kind of alluded to that earlier, and then I forgot to follow up on it. Yeah, so thanks. So yeah. So the nature of if you, as you saw in the visual, if you're throwing out, we had the 2-dimensional data that got compressed down to one-dimensional data, right? So if you're throwing out a dimension, what you're doing is you're sort of projecting onto this line, right? And by that, you actually see the coordinates change. So the values, the actual numerical values will change. And so they're no longer really identifiable as some specific attribute. Right? So
Yeah. Did you have a question?
No, I just want to make a same clarification that it's reduction of dimensions, not elimination of dimensions.
Yeah.
You don't get to, they're all done. Just new dimensions made from the old ones. You still need all the 50 if you want to make a prediction I've never seen before. Answer that.
right, yeah.
And we're gonna get into predictions. It's gonna get interesting about it. Yeah. So
Yeah.
glad you brought that up. But yeah, you're definitely abstract. Yeah, pretty much projected onto this abstract space where those dimensions don't really mean anything in human experience, and that's kind of like the thing too.
So once you get this correlation, if you have a new data point, does it have some sort of formula where you can just take that one row to get the values for the reduction, or do you need all of them?
I mean, can we iteratively, basically,
like if
update our
you already have this, like you already have this reduction on your data,
What do you say?
is there some sort of way to have a formula that you get a new set of 54 dimensions and you get the 3 math dimensions?
That's what I think you're asking. Like,
Not going backwards, I'm talking about you get a new row without knowing what the previous rows were. Can you have some formula that will reduce those to the 3 dimensions that would map the same?
So given that you already have, say, a PCA data, something's with PCA, right? And then you get this new row, and you're saying, hey, given that you already have the PCA, and you get this new row, can you iteratively basically map this onto PCA, or do you need like all of the original 1200 data, right? Is that what you're asking?
That's my question. Yeah.
So you have let's say we have 1200 rows. We turn it into PCA, okay, two columns. Then we get a new observation. We're like, oh hey,
1,200
we want to
rows, so 1,200 observations.
1200 observations, and we already turned it to PCA. So we got like 2-dimensional PCA, 1200 observations. Then we get like a new observation. And we're like, oh hey, we also want to go ahead and have this projected onto PCA. Given that you already have the PCA version, are you able to actually iteratively add it, or do you have to say no? We got to have 1201 and do the PCA all over with all the data.
Oh, it's like just incorporate a new observation?
Yeah, if you iteratively incorporate a new observation to PCA, you have to redo it all from all 1201.
Yeah, I don't see why not. Because really, at the heart of it, again, what it is a projection. So you can project. If you can project 1,200 points, then you can just use the same projection matrix to project that additional data point.
But let's say you don't have anything but just the PCA now. Like all you have now is just the PCA. You don't have the original data, and then you got a 54-dimensional.
If you just now have the original data, you have and you didn't keep anything from the process, then then you can't. But
Okay.
What I'm saying is that if you store the projection matrix, which you have to get under the hood to do this, so you have to write PCA basically yourself. You can't use a package. But there's a projection matrix that will that is being used to do the transformation that we call PCA. That same matrix can be applied to new data points and just project it onto the same space. And
it's like
now
if
it's PCA.
Because if you want to reduce it and then you want to use this reduced matrix to create a model, then you need a way. Like I don't think it would be good, like really usable if you need to the whole data again to be able to project new data to put it into the model.
Right, right. So I see what you're saying.
I mean, the new data, do you want to make predictions on the new
Yeah,
data?
it should be able to return a projection.
How would you say that? How would you say this compared to this reduced?
I'd be surprised if you could.
Really?
I'd be surprised. I know for a fact. I can
Is
look
you
into
build
it.
a model.
I'd be surprised.
So you have to
make
get the
projections,
projection.
or you make predictions against the
So you have to get into the package a little bit more,
That's the
maybe.
normal process.
Yeah. I'll take a look later and see.
You're
That's
not
the
always
question. I would imagine
constantly
you should be able
updating
to.
the model.
SK learning is
No,
no
no,
slouch. I would imagine they'll give you this.
What are you talking
I was
about?
talking
You said
about
something nice about a
reducing-
Python package.
Right.
Hey, the package is
The reduction is
We'll open that door
model.
later.
And the goal is to make predictions against the
Okay.
model, not update the model.
Updating is also important as well. Lots of data.
Anyway, yeah, you can do it. You just need to get the projection matrix.
Okay, so
That's a good question. I never actually thought about that. That's a good question. Yeah. Okay. So yeah. So again, yeah. So three columns retains 95% of our variance, and you have to take 11 more columns just to get 4.9% of it. Right? That's an idea of your diminishing returns. And of course, it's up to you to decide how much is enough. And we're going to test how much is enough by getting to our data. So right now, I want to start trying to visualize our data. Okay. I'm going to use PCA to do it. So first thing I'm doing is I'm going to go ahead and scale our data so it lies in that basically the interval of 0 and 1. And this kind of helps spread it out more on the graph. Okay? Not technically necessary, but it does make the graph a lot more beautiful.
This is not the scaling that I recommend.
No. Now I'm using a Python package because, yeah, why not?
But I don't know. Honestly, I don't know the right way to scale the data. From what I understand, the sort of standard way is called standardizing the data, which again, it shifts it so that it's centered around the origin, right? So the mean of every column is 0, and the standard deviation of every column is 1. Now, but that, I guess we had a conversation, Jared, we had this conversation where we talked about how that may not always be appropriate. So this question of scaling is, not something I think that we can clarify in this meeting. So how you should scale your data beforehand in order to get your results.
So having said all that, I scaled my data.
Against all my advice, just went ahead.
Yes. And so yeah, so
Again, results look fine.
it was also better than fine. But I just used the min-max scaler. It's built into sklearn. It's got a lot of different scalars too. Okay? So I just wrote just a quick function just to kind of, make it easy just to kind of scale on the fly, right? But it works similar to PCA. You instantiate an object, you fit your data to it, you transform it, and it'll project all the data onto the interval 0, okay? And so this is pretty much, and I kind of spit out the data frame just so you could see that all the data, all of our original data, is all in that range. And then I go ahead and just write a quick function also because I'm lazy and I don't want to keep instantiating a PCA object. To just take a PCA object and just basically create one and just transform the data just like a call out on the fly. Again, just a convenience function. And now I say, hey, you know what? I want to go ahead and try to graph this. We know that retaining only 2 columns gives us 90% of our variance. Okay, let's try to just hold on to 2 columns and graph it, right? That's a 2D graph. So first I project it onto PCA, and you can see here again we've got 1,200 rows, 2 columns, right? And again, these two columns, I can point out, are abstract projections. Okay? And of
So I
course,
think technically the new columns are linear combinations of the old columns, I think.
I won't lose any sleep over that distinction. They're abstract projections.
So it's what you were saying before. So
probably
the
true.
columns, it's not that the columns were like thrown out, but like
Yeah.
new columns were produced from the old columns essentially.
Well, yeah. No, that's what I'm saying. They're pretty much projections onto like abstract columns. You're not like throwing stuff out. You're basically deriving entirely new. Yeah. And of course, here we kind of confirm that our results are not correlated, right? So we just kind of do a quick correlation check on this, right?
So after the PCA, your correlations go to zero.
Yeah. You can see they're very close to zero, right? This point's around here.
So it's, again, talks about reorienting the data to just get rid of all the correlations. So now, uncorrelated data is ideal because there's no redundancy there.
And so now let's plot it. Let's see what this data looks like, right? So again, two-dimensional data, I'm going to plot it, and I'm going to color code. It's going to be a scatter plot. I'm going to color code it based on the heart condition. So we plot this and take a look. So this is interesting. So first thing we see is that our healthy heart, NSR is normal sinus rhythm, is very nicely and well separated from all of our unhealthy hearts, right? And again, this was originally 54-dimensional data, basically projected onto 2 dimensions. And then we can see here that our red and orange points, which are what? AFF, CHF, what was it, arterial? I forgot what these two were called.
Yeah, your predictions.
Something like that, yeah. And then CHF, you see they're pretty kind of close together, they're not easily separated, right? And then we can see that at least ARR is a little bit intermixed, but it's fairly decently separated. Now, look, spoiler alerts, this is kind of previewing some of the things we're going to see with our neural network we predicted, okay? So we're actually seeing a very cleanly separable boundary, so clean you can actually like draw a line through here and do manual predictions if you wanted to. And then we're seeing potential issues around predicting this area right here. And this will bear out in what follows. What we see right now, so we're getting a little bit of insight into basically what our data is and our classification, because we're interested in classifying by these 4 categories. And we're able to actually plot this despite the high dimension of the data.
But you see like all these, they're all like all these classifications, these different classes are splished all together.
Yeah.
So in a higher dimensional space, they might be separated. But projecting down in a 2-dimensional space smushes them together.
Although we're going to see some smushing even back. We're going to see neural networks with the original data too. But yeah.
So right question.
Is there some sort of severity to each of these? Like maybe the black one, is it the most severe one?
I don't know. Yeah, we didn't get into like the specific heart conditions and what they are.
Yeah, I mean, all I know is NSR is good, everything else isn't, but I don't really know like
NSR is normal sinus rhythm.
Yeah,
Yeah.
because since the black one is kind of like the most further away from healthy, I wonder if it has some sort of relation.
That's a good question. I didn't even think about
This
that.
is like, if you get one of these, you're still okay.
So pretty much you're kind of dead meat once you get into ARR territory.
Yeah, that's
Well,
right.
AR is arrhythmia. Arrhythmia can cause strokes.
CHF is the worst, congestive heart failure.
Oh, CHF's the worst?
Yeah, you had a heart attack.
So maybe that.
Okay. It would have been really cool if like the further away you were from
Yeah.
the heart, that would have been awesome. Okay. Well, thanks for ruining it for us.
That's what they would want to score, right?
Our pet theories. Okay, but cool. Okay, well, thank you.
You're welcome.
Science.
Science.
We don't confirm our bias.
Depends on how you do your science, but anyway. So, right.
You're welcome.
Yeah. So we kind of we see that the NSR is cleanly separated. Again, it's linear separable. I mean, the line was separated. The CHF, or was that ARR? ARR could potentially separate into something a little more complex than a line. Once you get into basically your AFF and CHF, right, orange and red spots, like just a heart
AKF, the
failure.
second most severe?
Huh?
So arterial fibrillation is an irregular heartbeat. So it could mean something bad and it could mean something that could potentially be, because a lot of people take medication to correct AFib.
Okay.
Okay. So untreated, yeah, it leads to problems. Yeah, but
close
the
as
thing
well.
is that AFib actually causes, fluctuations in, like if you put monitors on a person, you will see it. The rhythm of the heart is irregular, you'll be able to see it in the,
Wave,
yeah.
waveforms.
Yeah, so, but in just a heart failure, you have a heart attack,
Okay.
Is it always, is
Oh, sorry.
that maybe because it's always preceded by
so. Well,
That's why.
yeah,
It's quite different.
yeah, because it's irregular, it's not normal heartbeats.
Ah,
Always
okay.
preceded.
So
Yeah,
this might be why.
they're together.
Okay. Okay. So hey, I'll take this. So interesting. So thank you. I learned more about heart attacks than I kind of wanted.
So you know, they have to be ready.
Huh?
Be ready.
Get my will in order. Okay. And I see over here in our section, Justin thumbs his nose at PCA. So, okay. So,
This is the Jerry Springer portion.
okay.
Break out the alcohol
Okay.
model.
Okay.
No, okay,
Yeah, okay. So go ahead and.
The octagon here.
So this is what I did when I looked at after Ahmed will be extremely exuberant to point this out later. That after I looked at his PCA plot, I decided to do this. So he still wants to take credit. So I'm just, but so what I did is I did just a road search through the attributes and tried to predict normal sinus rhythm, based on a single attribute. And it's possible. So go ahead and scroll down.
That's basically
So
all
now-
about.
So this is when actually this is can I see the plot? Sure. Oh yeah. So this is my classification of normal sinus rhythm versus not normal sinus rhythm. But actually, this is from a stage in the talk where we were exploring just classifying the normal sinus rhythm versus not normal sinus rhythm, and so this is less relevant now because we took that part of the talk out. But anyway, so if you want to just classify normal sinus rhythm, one variable called NN tote will do the trick. Do a PCA needed. That's so dimension reduced to one dimension without PCA. So that's just by searching. So to me the lesson is like, well, before you try something fancy, maybe try something simple.
And this is the data that Frito-Lay and Philip Morris want, so they know who to target their ads to, because they have longer before their hearts give out, so they'll buy more chips and cigarettes. That makes sense.
That's one cynical and probably true way of looking at it. Yeah. I mean,
Is it info?
Longer.
I don't know. Maybe you should ask him so you can explain it. What is an input?
I don't know.
You just found
There's something called NN tote, and it predicts normal sinus rhythm.
Yeah, there's actually if you visit the page, I think also it came from Capital. They actually have a breakdown on what each of the columns actually is.
Yeah.
So I think I looked up NN tote, found out what it was, and promptly forgot again. Probably because it wasn't making a point for me, so I suddenly didn't remember. But the Capital should have all the breakdowns on what each of these people.
And apparently there are maybe a couple other attributes that predict normal sinus rhythm.
There's more than one.
So this is my classification algorithm. If NN tote is greater than 115, prediction is normal sinus rhythm. Else prediction is abnormal.
And then over here,
And so then I just wrote up a confusion matrix. So I get 100% accuracy. So you can talk about confusion matrices.
so a confusion matrix, for those of you who haven't are familiar, so it's a tool in machine learning that we use to figure out how well we classify things. And basically, so you can see right here, it's pretty much like symmetric. So you have each row is the actual classification of the data. The column is what you predicted. So when you look between any row and column intersection, the number here, which is essentially a ratio, you can cast as a percentage, tells you how accurately it was predicted. So the number of actual diseased hearts that are predicted as diseased is 100%. the number of normal hearts are predicted. Its normal is 100%. So you look at the diagonals, and the diagonals tell you what your prediction accuracy is. Off diagonals tell you where you misclassified and how. Does that make sense? Already? And this is useful because you don't want to just provide overall percentage, because you could have like very sparse data and basically misclassify and have a very high percentage because there's very few instances, say, like let's say our data was like 1,000 diseased hearts and 200 hearts that were normal size rhythm. You can have a machine, you have a really cheesy machine learning model, quote unquote, that just predicts everything's in diseased hearts, and you get a very high overall prediction, right? So yeah, hey, I've actually encountered that where I was dealing with sparse questionnaires, and literally like 90% of the data was like the questionnaires were false, and the machine learning algorithm was like, yeah, I'm predicting 0 for everything. Here you go, 90% accuracy. So you want to look at your confusion matrix because then you see, oh, yeah, I'm getting very high prediction here, but I'm getting very low prediction here, right? So you want to see how everything is predicted.
Yeah, so the diagonals and the off diagonals can be extremely important.
Yeah.
That's like how examples like a cancer detection algorithm or something like that, where like, well, cancer is very rare, right? So chances are it's not cancer, right? So say 99% chances it's not cancer, right? So you can classify everything as not cancer and be like, hey, accuracy is 99%. On the other hand, you just told 1% of people that they don't have cancer. Yeah. Incorrectly. So that the way the misclassification happens can be extremely crucial.
Yeah, we'll get into that when we look at the CHF versus AFF, because you'll kind of see where the off diagonals do matter. You had a question, Brian?
I just want to comment, also, sometimes, your goal should not be to get high accuracy all the time. You can overfit your model, and then when you go and try, your goal is to generalize the model from data.
Yes.
If you overfit it, then when you go to data that it's never seen before, it might do.
Yes. Yeah, that is 100% correct. And we'll even talk about cross-validation a little bit to try to avoid overfitting. You're absolutely correct. Yeah. And plus the penalty on misclassifying, right? If you classify non-cancerous as 99%, but you fail to classify cancerous, either 1% of the time, the cost of that misclassification is a lot higher than telling somebody mistakenly that they do have cancer, right? It's like you'd rather drop a lot of accuracy on the other side and have a few false positives than have somebody possibly die because they didn't seek treatment. So yeah, and there's also a cost to misclassification. So absolutely. Both
disconnected.
Huh?
Disconnected.
Well, okay. We'll check and see the complaints when I try to run. That was a run all. So my rebuttal to Justin's statement is so what? Because
That's a good one.
it is a good one because it's like, so what if it's just one column? PCA pretty much showed you there's a pattern. Whether it's one column is a pattern, whether it's several columns, who cares? We were visualizing data just to get insights. It happened to show us, hey, there's a classification. Okay, so yeah. And in fact, just an FYI, if you throw out the NN totes, you can still classify it under different columns. There's actually at least 2 columns that serve as classification. And again, PCA does show us that. So ultimately, it's just about exploring your data and yeah.
I'm not gonna argue. Sounds great, that's all.
Sounds great. So okay, so now we did see how in this data we had some issues with separability, right? Especially around these 2 points, right? AFF, CHF. It is a heart failure and was it arterial fibrillation? Okay. So let's go ahead and look at it in 3D, because in 3D we got one more dimension, right? So let's take a look and see if we get a little bit more. So here's a 3D plot, and we'll go ahead and just. So if we take a look at the 3D plot, we see that maybe there's a little bit more separation here, but we still see that basically our congestive heart failure and arterial fibrillation, they're still a bit intermixed. But at least in 3 dimensions, we kind of see maybe a way we kind of separate out a little bit better, and especially with our arrhythmia, right? So that gives us one more dimension doesn't give us
Black, right?
Black. Yes.
Black is really
Exactly. ARR is black. Yes.
black is really, it looks like it. You can see the separability and
Right.
how it can be separated out from the rest.
Right. So yeah. So I mean, even if we don't lose that much, it might be that some of the variance we lose, depending on the data, might be critical to maybe draw on some classifications. I see you squinting, Justin. What bothers you? Whenever you sequence, I always kind of worry about it.
Yes.
Yeah, yeah, okay, okay. So any questions?
Like
so far?
he's going to classify with one variable.
Don't pull out that. Any questions so far?
You see, right at this point, it takes two D slice, then you can separate them.
Oh, well, yeah, but by the time you're staring at the graph.
Right here.
Okay.
Pause it.
Okay. Actually, tell you what, let's.
So right there, that's just two variables.
Okay.
So now you can toggle it.
Here we go. Yeah, so yeah, we go ahead and just kind of tweak, like some of our parameters here, just kind of, rotate them a bit until you see something you like. So yeah, so where, do you remember, I don't suppose you remember your elevation azimuth, do you? Some kind of, is that what you're looking at, or do you want me to rerun that?
Move it to the left. Azimuth.
Azimuth, okay, azimuth to the left. Let's drag it a little bit over. Yeah. Enhance,
All the way to the
all the way to the left, okay.
order.
Huh?
Move it in order.
About 25, to about 25, about a quarter,
Around there.
yes.
So that's the 2D. That's the you say the 2D like that.
Oh, okay, I see what you're saying, yeah, you almost get a pretty decent boundary, linear boundary between ARR and your other disease points, right? Yeah. You kind of capture a little bit of it, but you actually have a pretty decent, yeah, it looks like there's almost a 2D boundary. You might miss a point or two, but yeah. So yeah. Yeah.
Maybe Gaussian. Maybe the Gaussian will separate the red, radial.
Potentially. I mean, complex enough curves should.
Just because the orange tends to be on the outside.
I mean, the radial kernel can separate anything. I mean, so you can have open.
When we watch 3D on the screen, we're just looking at an interactive projection into a 2D space anyways. So you probably could get, from some perspective, you might be able to get the same projection that you got before.
I mean, yeah. I mean, it's not good, but look at, I mean, yeah, you do have one extra column that's at least kind of factored into that projection though. So you are getting a little bit extra data you can classify off of, so.
We were doing that anyway with PCA.
Well, I was doing only two columns that are plotted 2 dimensions. Here, I actually went
Those are derived columns. Those are derived columns.
Yeah, and these are derived columns too, right? So this is 3 derived columns. The 2-dimensional is only 2 derived columns, right? So I have a little extra information. It adds some extra info, not a huge amount, but some of it could be critical to improving classification.
All right. So let's see it on
Okay. Okay. So yeah. So now we're going to go ahead and use a neural network and actually start predicting some stuff. Okay. So again, if you're not familiar with neural networks, they're just a machine learning algorithm. They're the ones who generally get the most attention nowadays. And essentially, they're simplified models of how the brain works, and very simplified.
And just a quick note is that even though we don't know what they add to, we've kind of lost the meaning of our attributes now, right? To some degree, that for if you're training a neural network model, maybe it doesn't matter, right? Because it's a black box anyway. Like you're not gonna, depending on what you're trying to do, right? The fact that we've sort of lost what our original attributes were for the PCA doesn't mean you can't train a neural network with it and get good results.
So yeah, and so here we just basically build a neural network. And again, sklearn already has packages. So all I'm doing is I'm just basically writing this as a convenience function. So the first thing I'm doing here, first line, and this is where we avoid the overfitting that Brian pointed out, is we break up our data. So we see here that I have X train, X test, Y train, Y test. What I'm doing here is I'm taking my data and I'm splitting it into training data and test data. The training data we use to build our neural network. The test data is something that we don't use to build a network. We kind of hold it away from it, and then we use it to test our network to see how well it classifies. So basically what we're doing is we're splitting our data. We're saying, hey, 30% of our data should be withheld and used only for testing, okay? And then the other 70% we're gonna train on. So the neural network will look at 70% of these 1,200 observations, build it, and then we're gonna test the 30% it never saw and see how well it predicted them. And this whole process is called cross-validation, okay? And then we just basically call the model, an NLP classifier is the model we're using, that's a neural network. We fit the model, then we call predictions, and then we generate a confusion matrix using basically against the test data that it never saw, okay? So we try to overfit as well, or we try to avoid overfitting, we don't want to overfit. And then I just round it just to make the numbers a little bit easier to see, okay? Now, the way this builds a neural network, there's a bit of a random element in how it builds a neural network. So it's going to start like a random seed, so that every time you build a neural network, it might build a little bit differently, and your accuracy might differ a little bit each time. Okay, so there is a bit of a random element, but overall, you're going to get pretty comparable performance. So far, so good. Okay, so first, let's go ahead and look at how our predictions. So again, we're trying to predict heart conditions from our data, and here we're going to go ahead and predict using our original data, which is 54 dimensions, right? So none of this has been reduced from PCA, okay? So we're going to go ahead and build it, and so this is pretty interesting. So here we see again, ARR is predicted with 98% accuracy. If you remember, ARR were the black points, right? They were the ones that were pretty decently separated, but not perfectly so, right? AFF.
That's using the full data set, right?
That's the full data set. We did not reduce PCA. Even though we viewed this in 2 dimensions, we're not using a full data set to show that our 2-dimensional projections do give us some insight. Here we see that AFF, right? Remember, that's one of our orange and red points, is 100%. But take a look at CHF. It's only 82%, right? And take a look. 18% of the time, CHF was misclassified as AFF. Remember, AFF and CHF were the orange and red points that were intermixed, right? Normal sinus rhythm, 100%. Now, again, there's a bit of a stochastic element. So if I run it again, I get slightly different results because it builds the neural network a little bit differently. But what we do still see is that our worst accuracy generally happens exactly where our plot showed us that these points were generally intermixed, right? And our best accuracy hits at NSR, right? So here again, 96, 74, that pretty much sucks, right? But again, the off diagonal tells a story. Hey, of this 74%, 24 misclassified as AFF. The orange and red points.
The orange and red ones are all
Yeah.
smushed together, right?
Yes, the orange and red
So
ones.
it's a hard time.
Exactly, right? And again, yeah. And again, where we land on a build, well, sometimes get pretty decent results, but generally speaking, our worst accuracies are going to happen exactly where our plot showed us that these points were not easily separable. And remember, these plots were again in 2D, but even with the original data, remember, this isn't a 2D data, this is the original data, not changed for PCA, and that's showing us where we're running into, where we're struggling. So far, so good. And then we just kind of look at it in 14D. 14 dimensions is basically where we retain 99% of our variance, 99.9%. And again, we see here that we do a fairly decent job, right? Again, we tend to struggle a little bit more in this area, but, you know, we're not too bad. And it looks like we're getting a little bit better than what we are in a 54-dimensional case, although, again, we'd have to run a large number of samples and make sure it's just not a statistical artifact, right? But again, we see at least where we generally struggle. And then again, with two dimensions, this is the PCA that we had plotted, only 2 dimensions, we can see here this, yeah, really dismal, right? Of course, NSR is great because NSR is very clearly separable. So even in 2 dimensions, we still get 100% on NSR. We're pretty good at ARR. But again, the central area is where we struggle. We struggle a lot more than we did up ahead. But in every case, we see that we struggle in these areas, and best prediction is always around NSR. Questions? So these are the predictions of the neural network, and they're borne out by what our plots show. So our plots at least gave us a preview in areas where we may struggle with our predictions. And that's another benefit to at least being able to plot it.
So the PCA actually made a
In this case, it looks like it did. We want to run it like a lot more and average out the results just to make sure we're not like getting statistical artifacts, but at least it looks like the central areas are predicted a little bit better. And we actually were wondering about that. So we're like, so why would this predict better in a 14D case versus 54D? And we were wondering, I don't know, was it maybe getting rid of some noise? We weren't sure, we kind of speculated. But, so,
There are several,
A noise reduction.
there are several capital examples of which reducing PCA actually improve more.
okay.
It's not just improve reduce the computation component, also improve.
Okay. And that's what we're kind of seeing here, right? At least with 14D, when you drop it and maintain 99.9%, you actually seem to do a little bit better. 2D definitely doesn't do better, but here at least, especially around these areas, it definitely does do better. And that was kind of like we were wondering about. So we're saying this is pretty much because of noise and, or,
No, I'm getting rid of correlated.
okay. Because it's probably doubly counting with the correlations,
Yes.
not,
So
okay.
it's here, it's getting rid of the artificial overweighting.
Okay. So the key is just being able to get rid of just enough to do that without losing any real information. Okay.
We did Google capital search.
Cabal,
Dimensionality reduction of correlations.
I'm gonna go ahead and bookmark this. We're actually almost done anyway, but yeah, I'm gonna bookmark this because I got me some reading to do. Because we were kind of wondering about this, so that's actually, it's good to have some insights, so.
It's not one of those, but there was one example where it showed getting rid of noises.
Oh, that's cool, at least not on the search term like it
I
did.
think it was smoking and lung disease.
Smoking.
The result was cancer and non-cancer.
This is-
There was a bunch of variables, and they got removed some of the predictions.
I'll go ahead and do a search. Cool. Okay, cool, yeah, I'm gonna definitely dig into that a little bit more. Thanks, Kai, because we were wondering about that. And we're actually pretty much at the end of this one. So, again, we kind of see the Ray talked through the performance, right? Poor performance in 2D, right? Original data, we still had worse performance around the central areas. So at least we understood that. 14D seemed to give us actually better performance. And again, NSR, the most several points were really where we had the better performance. And just a quick recap, right? PCA can reduce the dimensions of your data, or retain a lot of your variance. Once you reduce your dimensions, you actually have a chance of plotting your data and seeing some insights visually. And again, like we mentioned before, right? You're not basically removing columns, you're projecting your data onto entirely new columns so that you're kind of looking at it sort of abstract axes at that point in time, or abstract dimensions. And yeah, that's about it. Do we have any questions on anything? Cool. Again, for those of you interested, you can scan a QR code. That's gonna take you to our LinkedIn, and from there, we have the link to this collab if you wanna use it. Yes.
Can you in the future, maybe instead of just having the QR code, also add the link maybe next to it or?
Sure, I can do that too.
So
Yeah.
we can just do it from our computers if we're
Sure.
following along.
Yeah, the main reason I didn't because the link looks something like this, and I wasn't sure if you felt like typing all of this.
I mean, you
But
could
yeah.
just put link and then, you
Yeah.
put
I'm not-
the word link and then hyperlink it, like.
Okay. Sure. Yeah, I can definitely do that. Cool. So yeah, so that pretty much wraps it up for PCA. Yeah, I mean, pretty much, yeah. So guys wanna hang around, ask questions, dive into the weeds on anything, just chat away, eat pizza.
We'll make one last note, which is, I didn't even mention, I meant to at least mention it, that principal component analysis is, the actual computation is a eigenvector, eigenvalue problem. So in case you're doing your algebra, it's basically you find the eigenvectors of the correlation matrix. Or the covariance matrix, if you're going that route. Which actually leads me to point two that I want to make sure to mention, which is that the difference between correlation and covariance matrix is that of scaling. So in both cases, the data is centered before you do the PCA. But for the if you use the covariance matrix, it's also scaled to have standard deviation 1. But if you don't, then it's the covariance. You're actually using the covariance matrix. So it's connected to how the data is scaled. So I don't know exactly how this works in the package, but what I would do is just do my scaling ahead of time. But it won't standardize, meaning it won't make your standard deviations 1 automatically. sklearn won't, but it will center automatically. Yeah. So that's it.
I try to avoid using the E word in my talk, so. Okay. Again, just a reminder, you scan this QR code, it takes you to a form. If you want to give us your thoughts, what you want to hear about in the future, what you thought went well, what didn't went well, can help us refine and improve our talks. So definitely feel free to do that. Yes.